Hello friends, welcome back to my channel Chemistry with DB. In this video I'm going to explain the sigma and pi bonds and also the reactivity aspect of alkanes and alkenes as to why alkanes are very unreactive and alkenes are fairly reactive. So we'll start with a little bit of a background, right, or a foundation we can say about what are covalent bonds, what is an orbital, then I'm explaining the s and p orbitals, what are sigma and pi bonds, how do these form, and also about the relative strength of these two sigma and pi bonds. So for the background, covalent bond, co means sharing. So therefore covalent bond is a kind of an electron sharing arrangement wherein two atoms share one or more electrons with each other by overlap of their orbitals. Now what is an orbital? It's an area around the nucleus in an atom where there is a maximum probability of finding an electron. Now let's see what are S and P subshells, So S subshell has, it has got only one orbital and it can hold up to 2 electrons. On the other hand, a P subshell can hold up to 6 electrons in its 3 p orbitals. And those 3 orbitals are shown here. So the first one is a px, second is a py, and the third one is a pz. Now s orbitals are spherical in shape, while the p orbitals are dumbbell shape. So the 3 p orbitals, what they are arranged as is the px is, you can imagine it as it's parallel to the x-axis. Py on the other hand, it's parallel to the y-axis. And pz on the other hand, it is at 90 degree to these two, px and py. So this is how the 3p orbitals are arranged. Now let's see what are the different types of bonds which are possible, which are sigma and pi bonds. Now sigma bonds are formed whenever there is an s overlap, that means two s orbitals overlap, or in this manner, and or one s and one p orbitals overlap, which would look like this, or when two p orbitals overlap in a horizontal manner. Now you can see that the red part shows where the shared pair of electron is going to be, and you can see that this is a localized electron pair, and this will have a strong attraction from the nuclei of the two atoms, the green ones. So in all of these you can see that the nuclei of the atoms involved would have a very strong attraction for this shared pair of electron, which is placed right in between the two. This is the reason that sigma bonds are extremely hard to break and they are very strong. Now let's see how does a pi bond come into play. So pi bond is formed through a sideways overlap of 2p orbitals, which is like this, py. Now you can see that the shared area is the pi bond, and you can see that the shared electrons, that pi bond, the electrons here are away from the nuclei. As a result, there would be less attraction from the nuclei of the two atoms for this shared pair of electrons. Now, because of this sideways overlap, this gives rise to an area of very high electron density above and below the plane of the molecule or the bond. So this we can call it as a electron cloud, which is a now electron cloud here, this is going to attract electrophiles which are positively charged species which are attracted to an area of high electron density. Now, in a nutshell, here are some notes for you that in a pi bond, sideways overlap of two p orbitals results in an electron cloud above and below the plane of the molecule. The shared pair of electrons is at a distance from the nuclei of the two atoms, unlike in case of sigma where it was right in between. Therefore, less attraction from the two nuclei. This is the reason that the pi bond is weaker than the sigma and it breaks relatively more easily. This is the reason that alkenes end up being far more reactive than alkanes, because in case of an alkene there are two bonds, one is a sigma, other is a pi, and it's the pi bond which breaks whenever an alkene reacts. The electron rich cloud attracts electrophiles, so therefore the reactions take place through electrophilic addition. Also, very important aspect that C double bond C, when there are two sigma and pi bonds together between the two carbon atoms, or it does not allow rotation of the groups around it. So I am creating more videos on the electrophilic addition aspect of alkenes, and also as to why the alkenes allow geometric isomerism to occur. I hope you liked this video, and in case you liked it, then please like, share, and subscribe. And also look at the links of my other videos at the bottom of this page. And I look forward to see you on my next videos. Bye. Take care.